I start today with, I guess, the second part of Peter Olver's tutorial on invariance and symmetry and cognition.
Thank you. So sorry for the delay. I was paying attention to yesterday's schedule. Sitting there waiting for them to start. So where we left off is I started to talk about joint invariance. So we started to do various geometries, so distances, angles, areas, and then this interesting cross ratio for the projective group. And one of the immediate places where this is used, and this is quite common in image processing, is in terms of histograms. So suppose I have a bunch of points, say the square, then I can of course write down the distances between the points, and I can look at that as a histogram. So in this case it's 4 1s and 2 square root of 2's. And it's certainly invariant under rigid motion, so if two sets of points have different distance histograms, they're certainly not equivalent under a rigid motion. And so that's just a thing of a histogram. So they have the same distance histogram, and then the question arises, does the distance histogram uniquely determine the set of points? So this would be nice to go back. See if anyone who doesn't know want to guess. So the answer is, and this is a result of a former student of mine, Mimi Boutin and Gregor Kemper in 2004, the answer is yes for most sets of points, but there are some exceptions. Technically, the set of exceptions, if you put the right structure on it, is an algebraic subvariety of the set of all possible point configurations. And so you might ask, well, what do the exceptions look like? So your immediate idea might be something like a square, which is rigid, but it doesn't take long to realize there's only one way to reassemble them. I sometimes think of this as the Tinker Toy problem, for those of you old enough to remember Tinker Toys, and you have to put them back together. So if you have four bits of wood of length 1 and 2 of the square root of 2, that's the only way to put them together to form a point configuration. So that's yes. Here's an example where it's not unique. So both of these, the kite and the trapezoid, have the same distance histogram given at the bottom. And to see how you go from one to the other, if I disconnect this vertical bar and then rotate this point down to here and then reconnect them, and I've arranged it so this is exactly the same distance, then it's clear that they have the same distance histogram. But they're certainly not rigidly equivalent. But generically, they do uniquely determine the point. So for practical purposes, we could use the histogram, the distance histogram as a unique method of reconstructing the points.
And how does this depend, how does the degeneracy depend on dimension?
So it's an algebraic subvariety given by several polynomial equations. So it's a forgotten offhand. I think it's codimension 1, but I've forgotten offhand what.
So in high dimensions, then degeneracy increases very rapidly.
So your chances of hitting a degenerate configuration are basically 0.
Even in high dimensions?
Even in high dimensions, yeah. So it's always an algebraic variety of lower dimensions than the space of all possible point configurations.
Sorry. Oh no, go ahead. Can you move continuously between them?
So no, I think the answer to that is no. They're the ones that are degenerate discrete, so there is no continuous motion. This kite is rigid under deformations. But if so that's why I have to disconnect the bar, flip the point over, reconnect in order to get the degeneracy, and that's true in general. Yes?
This is a non-technical question. Is part of your postulate here that the visual system uses distance histograms to identify rigid motion?
I'm not postulating that.
Okay. Well, I mean, maybe I can draw it.
Maybe
we can come back to this later. I can draw it.
Who knows more about the visual system might postulate. I'm not going to postulate that.
Okay.
It's
an interesting hypothesis.
But they are used very often, these invariant histograms, so methods from image processing like SIFT and other things with various acronyms are based on simple histograms of quantities, distances, areas, angles, and so on. And they're used quite extensively in classifying objects. As I said, you can do this with other. So actually, this is my favorite short paper. So even on the line, the answer is no. There was actually a paper which claimed to prove the theorem that the answer was yes, And my favorite short paper, this is basically the entire paper, were two sets of points with the same distance histogram line on the line. Of course, it had an introduction and a conclusion, but that's the entire paper.
Why is it 2 pages long?
I think the first paragraph, the introductory paragraph, is on page 378, and this is on page 372. It's just the way the journal was configured. Okay. One of the other things that I've proposed, but hasn't really been extensively used, is using distances to uniquely characterize curves, and I'll get to some other methods. But one of them is there's a method. Suppose I have 4 points on a curve, then there are 6 interpoint distances, and hence you have basically 6 functions of 4 variables if you think of the points moving independently around the curve. And so generically there should be 2 algebraic relations relating them, these 6 distances. One of these is well known as something known as the Cayley-Menger syzygy. So this was written down by Cayley when he was something like 18 in his very first paper. The question was, if I give you a bunch of distances, if I give you these 6 distances, when is the point configuration planar? And the answer is true if and only if this determinant vanishes. And this has led to a whole subject area known as distance geometry that's become very popular recently. So one of these is universal. The other one actually uniquely determines the curve up to equivalence, up to rigid motion. As I said, this hasn't been practically applied yet. There's area ones. And then another thing we did was looking at what happens if you take a curve and you do a limiting curve distance histogram. So you take the distances between all the points and write that down as a cumulative histogram. What's the limit? And so you get these expressions, something like this. So this is the length of the intersection of the curve with a disk of radius r divided by the total length of the curve, which is integrated ds. And this is a simple example of something that's become quite popular in image processing, known as an integral invariant, as opposed to the differential invariance I'll talk about in a little bit. And some other interesting integral invariants are what's known as the circular area invariant. So this has been analyzed quite a bit by now a colleague of mine, Jeff Calder, who's working on this project with both, I'll describe at the end, and his advisor, Selina Sadoglu. So this is, you take a curve, and at each point you draw a circle, a disk around it, and you measure the area inside the curve. So we're thinking of a closed curve. And that's clearly rigidly invariant, because if I move the curve, the disk stays the same size. And so that does, in certain situations, uniquely determine the curve. And we're using it in the sort of 3-dimensional version. So this is a bone fragment. I'll come back to these later, why we're interested in these. But something called the spherical volume invariant, where you take a sphere and intersect it of radius r and a point. And the r you're allowed to vary, and depending on the size of r, you get interesting geometric information. In particular, these break edges are quite well characterized by this invariant, by the size of the invariant. And you can see that because if you're at a point where it's not a break, the sphere the surface is more or less flat modulo some curvature. And so the volume inside is about half the total volume. Whereas if you're at a break angle, the volume inside is significantly less, or if it's an angle this way, significantly more than half the volume.
So what is the invariant again?
So the invariant is so at each point on the surface, you take a sphere you fix a radius r, you take a sphere, intersect that with the interior, and measure the volume of that.
Of the intersection.
Of the intersection of the sphere. So
Surely
the part of the bone, in this case, that's inside the sphere is measured.
Surely uniqueness will depend to a significant degree on the radius of the sphere.
That's right. So it's a sort of a multi-scale. So depending on the radius of the sphere, one gets different values. Of course, if the sphere is gigantic, it encloses the entire bone, and you just get the volume of the bone.
So another question.
Yeah.
Do you work over real numbers or complex numbers?
Real.
Real numbers.
All this is real.
And then
one could do complex, but I don't.
So in the case of the syzygies that you were discussing, when you obtain the equation of the curve, you say the other ones are related by rigid body transformations.
That's right. Yeah.
But you solve polynomials how do you know they are all by transformations? Because you can alter the coefficients of polynomials, you can get automorphisms.
Okay, so they're not necessarily polynomial curves, these are smooth curves.
But you said you write them as solutions to polynomials. Isn't that right?
Right. So that polynomial uniquely determines the curve up to rigid motion.
Why is it up to rigid motion necessarily? Because
Well,
you
it's
can have many different transformations.
Yeah, but the transformations all preserve the distances. So it's clear that that's invariant under rigid motions. And the fact that it uniquely determines the curve is a theorem that I don't want to get into proving. It's a theorem in differential equations, actually. It's not a theorem in algebra. Yeah.
What about the difference between convex surfaces and concave surfaces? Convexity and concavity.
Well, the convexity and the concavity is indicated by the amount, the fraction of the sphere that's inside. So if it's convex, there's less than half of the sphere is inside. Locally, if it's concave, there's more than half. In fact, with further work, you can use related invariance to this to get good approximations to the curvature, the principal curvatures. It's the Gaussian mean curvature of the surface. This is some work that my wife Cherry Shackelman did with a former undergrad. She's now a graduate student of Brown, and they used these distance histograms in trying to see if they could distinguish moles from melanomas based on the outlines. So there's a typical distance histogram of a melanoma. There's one of a mole. And when they graphed them initially, it looked like there wasn't much difference. So these are cumulative distance histograms. But when they looked at the shapes of these, they found that the shapes of the cumulative distance histograms of the melanomas were much more convoluted in some sense than the moles, which were more monotone. And so they got some reasonably good results on characterizing it. Not something that you would want to trust this in lieu of a professional, but at least there's some interest. And it seems like combining this with other things that I'll say in a minute, sort of a set of tools based on various types of invariance, in this case invariant histograms, seems like one good way to go in trying to distinguish things like this. So the last topic before I get on to the further applications is I want to talk a little bit about differential invariance. So now I'm going to bring in some calculus. So far it's been pretty much algebra. And we've already heard lots of talks about curvature yesterday, so I don't have to remind everybody what curvature is. It's a measure of bendiness in some sense. It's the reciprocal of the radius of the osculating circle. The only reason I like to draw this is all mathematicians draw the osculating circle wrong. They have the curve almost always on one side of the osculating circle, but that's false. This is the generic situation. The curve goes from the inside to the outside of the osculating circle. I always drew it wrong up until about 10 years ago when somebody pointed this out to me. So there's a whole calculus underlying this, but this is a very classical theorem that besides the curvature, there's a whole series of higher-ordered Euclidean differential invariants, and these are given by the successive derivatives of curvature with respect to arc length. And this is a complete list of differential invariants. So these are invariants that depend on the derivatives of the curve and are unchanged by rigid motion. So the curvature, of course, we know is that, but its derivative with respect to arc length, the rate of change of the curvature, is also invariant, higher derivative. So you get a theorem like this, and this is a special case of a very general class of theorems. There's the formulas. For instance, we heard about similar, what was this called? Absolute, was this the absolute curvature yesterday?
Absolute and scaled curvature.
Absolute, and so this one you called scaled.
It wasn't me, but it was, the regular curvature is absolute curvature.
Okay, so this is the similar differential invariant absolute, or whatever you want to call it. It's just a ratio of the derivative of curvature with respect to arc length and curvature. That's the simplest differential invariant for similarity geometry. And here's the corresponding arc length. And one can do the same thing. These are well-known formulas for equiaffine geometry. This is the equiaffine curvature, the equiaffine arc length, very similar theorem. And this is even known, there's some horrendous formula involving 7th order derivatives that defines what's known as the projective curvature of a curve. So, of course, we saw with the duck and rabbit yesterday that it has its problems, but if you didn't have noise, these do also end up uniquely characterizing plane curves up to projective transformation, but they're just almost impossible to compute in any reasonable way. So here's a question for the audience. What everyday device, quite a few of you used it, maybe even getting here, it's none of these. So this is a quiz I give to students. Anybody have an idea? There's a device almost all of us use most days, unless we walk.
Your phone?
Steering wheel?
GPS.
Steering wheel, yeah. So a steering wheel measures curvature, right? Because the more the road curves, the more you turn the steering wheel. Okay, so if you go around this racetrack, say, you get this graph of curvature as a function of time. You can connect this up to where the different bits of curvature are. And the question is, suppose I give you this graph, can you uniquely reconstruct the racetrack? Okay.
Yes.
Anyone want to volunteer? Yes?
Yes.
No?
Yes.
Yes.
Okay, well, there's a hint. What if I drive at a different speed around the racetrack?
Up to scale.
Oh.
So actually, if you think about it for a little bit, what you realize is you should not measure curvature as a function of time, you should measure curvature as a function of distance along the racetrack. Okay? And then the answer is yes. So this is a very classical theorem that if you know the formula for kappa as a function of arc length, you can uniquely reconstruct the racetrack. This is another theorem in differential equations to reconstruct it up to rigid motion, because of course if I rigidly transform I rotate or translate the racetrack, I get exactly the same graph.
But can I ask a sort of a comment in that context, or maybe a question?
Sure.
You still nevertheless can't say, for example, if a curve is closed or not if I'm just given the curvature and torsion.
Let's see, you have the integral of kappa ds give you 2 pi. Yeah.
But can you
Is that necessary and sufficient?
can you guarantee that the curve is actually closed if I give you the curvature? In 3 dimensions, it's certainly probably not true that if I'm given the curvature and the torsion, but I know whether the curve is closed.
I think that's right. But in 2 dimensions, I seem to recall it is true. But I'm not 100%
in 2 dimensions, it is
sure.
true. Okay.
I seem to recall that. The one thing you don't know from this is you could start at a different point of the racetrack, and then of course the graph would translate. So there's still an ambiguity. So it depends on where you start when you go around, when you're driving around. So here's the ambiguity. So the yellow car starts here, the red car starts here. So these are the 2 graphs. And of course, they're the same modulo a translation in S. So some years ago, we proposed to, instead of looking at kappa as a function of S, to take the 2 simplest differential invariants, kappa and d kappa by ds. And with a little work, you can see that if you know what we call the signature curve, so as you go around the racetrack, you graph both kappa and kappa s, and you get something that looks like this. And this does, for sufficiently, so this is called the invariant signature. And there's a theorem, regular, and I don't, if you ask me after, most curves are regular. 2 regular curves are related by a group transformation, in this case a rigid motion, if and only if they have the same invariant signatures. So this was a proposal we made in a paper in 1998.
When you mean the same invariant signatures, you're talking about the entire curve?
Yeah, so this entire curve, yes.
Not the zeros and...
Not the zeros and so on, the entire curve. So the signature means the signature curve, the full curve.
And is this the only way to construct an invariant?
Only.
Maybe something that I'm missing is you're saying d kappa ds is a function of kappa, but I could have had higher derivatives of kappa.
Okay, so that gets it. So why do I only need d kappa ds and not the higher derivatives? Well, I had a slide like this, but I thought someone was going to catch me on that. So if I have kappa s as a function of kappa, and I differentiate it, then I immediately know what kappa ss is.
Thank you.
And so I don't need these higher order invariants, I only need these two. So this is part of a general machinery, and this holds for not just the Euclidean group, any of those groups that I showed, or any other group where you have where you know about the differential invariance, you can construct a corresponding invariant signature with the same properties. And this is a general theorem that goes back to Élie Cartan when he solved the equivalence problem of when are two submanifolds equivalent under a group transformation. So this is a reinterpretation of Cartan's result. And we've used this quite successfully. Oh, let's see what I have next. Oh, so here's some other types of signatures coming up. For curves in space, one needs kappa, kappa s of torsion. It's a little exercise to see why you don't need tau s to construct a signature. For surfaces, you can either do it in terms of Gaussian mean curvature and certain invariant derivatives of them, or purely in terms of mean curvature. So there's various types of signatures. This is, I'll show you where this is used. This is something we're looking at in the context of those bones, but we have not, no one has actually used these seriously, and it may be that these are just too complicated to make significant use of. But at least theoretically, there are these differential invariant signatures. And all of this is, over the past 20 years or so, I've been developing a new approach to moving frames, so-called equivariant moving frames. And this gives a very systematic algorithm for almost everything I've been saying about constructing joint invariants, differential invariants, invariant differential forms, invariant variational problems can be done systematically and algorithmically using this method of moving frames. I'm not going to go into this here. Including symmetry preserving numerical methods. So of course, when you want to apply these differential invariants to practical objects, you don't have the nice smooth curves. You can maybe interpolate them by splines or something. But we like to use invariant numerical schemes, and the simplest one is based on Heron's formula for the radius of a circle through 3 points. So we approximate the curvature at the point B by choosing two nearby points, drawing a circle through it, and using this formula. And that's an invariant, because everything is just purely based on distances. This is clearly an invariant approximation to the curvature of the point. So those are the type of numerics when I show you the pictures coming up in a second. Yeah. So here's some examples of signatures. And this gets into a little bit of what was being discussed yesterday about shapes and when are shapes near each other. So one possible proposal is that you look at the signatures and compare the signatures rather than the shapes directly. So this one is almost circular. If it was exactly circular, the signature would be a single point. This curvature would be constant, and kappa s would be 0. So this is close to being a single point, and this is a reflection of this being almost circular. This one has an approximate threefold symmetry. This is the Euclidean signature, and if it were exact threefold symmetry, the signature will go exactly 3 times on top of itself. This is the corresponding equiaffine signature. This is equiaffine curvature and its derivative. And if I subject this shape to an equiaffine, so you could think of it as a projective transformation or approximation or projective transformation, I get this. And certainly to our eye, these two shapes look very different. The Euclidean signature has changed quite a bit, but the affine signature is exactly the same.
So the last picture and the middle one also, these are singular curves. And
well, they self-intersect. Yeah, that's very common with the signatures.
So what if you have more interesting singularity loci, like sine of 1 over x or something?
Yeah, you can have all sorts of things. So well, we'll see. Hold on, and you'll see even worse examples of intersecting signatures. So this is a project I gave to my student at the time. This is 20 years ago now, and we digitized a bunch of stuff he bought at the hardware store. So these are 2 different pictures of a nut with 4-fold symmetry. So you see this in this. If it were exact 4-fold symmetry, these would be exactly 4 times on top of each other. If you want to add in the reflectional symmetry, basically you have to graph absolute value of kappa s, and then you get 8-fold symmetry coming in here. And this is very similar, whereas these 2 are very different. And then we see, but we're seeing local symmetries also in the sense that I described before. For instance, here there's a local symmetry that's being, sorry, no, this is a straight line. That's there. Now this bit where we go around here is this local 2-fold symmetry coming in here. Okay, and then also Cherry and her student also did this with breast tumors. They also did moles and melanomas, and they got sort of very different types of signatures. The benign ones, the signatures were much less convoluted than the malignant ones. And so again, they did statistical analysis of this. So the last topic, let's see, what do I have? 10 minutes, 15 minutes?
15,
15.
20.
Okay.
Yeah, we can go sometime between 9:45.
Okay, so one thing I've got very involved in recently is reassembling broken objects, particularly three types. So jigsaw puzzles, broken eggshells, and broken bones. So I'll explain all of these as we go along, and this is what we're most recently working in. So, this was a movie, but I don't think I'm going to show it. But somebody assembling a jigsaw puzzle. So this is an actual example that we did. So this was with an undergraduate student of mine named Dan Hoff a few years ago. And Dan, we worked on a more theoretical project with signature curves initially and wrote a paper up on that. And then he had about 3 or 4 months left in his undergraduate career before he graduated, and he asked for something else to look at, and I had known about a couple of papers on reassembling jigsaw puzzles, so I suggested to him, why don't you look at this, not really expecting very much. And so Dan goes off, and I hadn't realized he was a big jigsaw puzzle fanatic as a kid. So he went off and he bought a couple of jigsaw puzzles. So this is one you can get on Amazon for I think it's about 20 bucks, the Baffler Nonagon. And because we're only working with the shapes, we really like this one because there's no picture, so there's no way of matching the pieces based on pictures that are on them, because they all have different colors. And also they have very unusual shapes. And I know why I wanted to show the movie. I'm talking. So one of the things you see, if you or I go to assemble a puzzle, of course, what do? Well, typically we look for edges. So you see gradually the edges start being done because we recognize straight edges of it. Now, the signature method that I'm going to describe is kind of the opposite. It works from the inside out. So it likes the most convoluted pieces, the most interesting pieces, and gradually works with those. So here are the 67 pieces of the Baffler Nonagon. And I'll describe a little bit the algorithm, but with some tweaking of various parameters, we were able to do complete reconstruction of this, and this amazed me. So he went off and started doing this, and then he would come back, oh, I've managed to put 2 pieces together, 5 pieces together, and so on. Within like a month, he had the algorithm working, where for this one in particular, it worked extremely well. So that's the reassembly, and it starts with one of the interior pieces, and it gradually works its way out, and it does the... We don't like the straight edges because they don't have any interesting signature. They're basically constant curvature, zero curvature. And that's what it looks like reassembled in real life. So this takes about an hour on a laptop in the MATLAB Pro that he wrote. I still don't know how long it would take a human being to do this without knowing anything about the puzzle. So when you have the box, I don't have the back of the box, but the back of the box has a good fraction of the puzzle already assembled. So when I tested my adult children, my son is a mathematician, he cheated, he looked at the back of the box. So he did it in 20 minutes, but I don't count that. Anyway, so let me briefly say how we're doing this. So the first part is, of course, to digitally photograph and smooth the puzzle pieces. So you have to be quite accurate in your photograph, the way the algorithm works. And the smoothing turned out to be a little bit challenging, and we came up with kind of ad hoc smoothing technique. So we tried some of the well-known smoothing techniques like curve shortening flow and so on, and they erased too many of the important features too rapidly. So we ended up with this kind of ad hoc smoothing technique based on spline interpolation and then respacing the points to be equally spaced and applying that many times. So that was the first one. So then we numerically computed invariant signatures, but of course you don't want to match the entire piece, so you don't want the entire signature. So we have a method of splitting up the edges of the pieces into different parts. I'll explain that in a second. And we computed those numerically by using those invariant numerical algorithms. And then we compared the signatures, and I'll discuss what we mean by comparing to find the potential fits, and then we put them together and repeat. Now, in a lot of the puzzle literature, there's a lot of stuff about what happens if you make a mistake. How do you backtrack and figure out where to go? So I was really worried. Many things worried me when he started this that I was not expecting much. But I was worried about the backtracking problem. But the algorithm proved to be so successful with the Baffler and a couple of other ones we did, we never got into backtracking about it. So that's okay. So how do we localize it? So we ended up chopping up the edges into something. So this is invariant, what we call a bivertex arc. So in curve geometry, a vertex is just an extreme point of curvature, or slightly more generally, a place where the derivative of curvature vanishes. So a bivertex arc is just an arc between two zeros of the derivative of curvature. And if you look at it at the signature level, it's just one signal arc. Remember, those signatures would wrap around and around and around. So we just look at single arcs of them. So we split up the curve that way, and we start comparing bivertex arcs. And if we get enough of them matching under the same rigid motion, then that's a potential match for the two pieces. So that's sort of the preliminary step. So that's the splitting it up. Oh, this is Dan Hoff. This is where the paper appeared. And then we want to compare this. So how are we comparing them? Well, there's all kinds of methods for comparing shapes. Hausdorff distance, Earth mover's distance, Monkenschdorf. The one we ended up working the best was something based on a sort of electrostatic or gravitational attraction. So I think of the two arcs of the signature curves as masses or as oppositely charged wires. Then the higher their mutual attraction, well, of course, if they cross, there's an infinite. So you have to get rid of the infinities by adding in a small fraction when you small results of the fraction. Or equivalently, you're really thinking of them because ultimately it's all numerical. It's just a bunch of points. And if you look at the mutual gravitational attraction of those considered as just a bunch of point masses, then the higher the attraction, the closer they are together. And that proved to be a very useful. That seemed to do the best for these purposes for comparing them.
Why not use like a spring between?
Well, try springs. Well, we have something like a spring in the next slide. We didn't use springs here. Well, so when you do gravitational attraction, of course, you have a potential, and it doesn't have to be 1 over r. It could be 1 over r to whatever power you like. So we played. That was one of the parameters we played around with, was the power, and I forget the one that Dan chose that did the best for the jigsaw puzzles. But it was something near 1, not quite 1.
You're starting to interpret just today. You should wrap up in the next few minutes.
Yeah. Okay. Okay, and so then we had a method of piece locking. So here's the minimum to try to get the pieces matched as closely as possible. And this proved to be very useful because if you make a small mistake initially, it quickly propagates and you get stuck. Okay, so 2 last things in the last 2 minutes. So after I did this, I sent the paper around to a few people I knew who had worked in jigsaw puzzles, and one of them, a guy named Marshall Byrne, who used to be at Xerox PARC, said, oh, I have this data of a broken ostrich egg shell that I've never been able to do much with. So in another project, we worked on this, and we did pretty well with synthetic, here's a spherical or ellipsoidal puzzle. So we did pretty well with that. For the actual egg pieces that he showed me, the data wasn't very good, and there's lots of things. So with a lot of hand-holding, we did something that was halfway reasonable. This is, I don't have time to do this. This is, there's money to be made in reassembling broken eggs. There's something called the elephant bird that used to live in Madagascar, which is much bigger. This is an ostrich, this is an elephant bird. And here, so there's a wonderful video of a very young David Attenborough reassembling an elephant bird eggshell. And so I don't have time to show that. And on so a completed elephant bird reassembled egg recently sold for $100,000. So there's money to be made. Of course, there's things in archaeology, pottery, but the last thing we've been working on, so I got involved with a group in our anthropology department who were very interested in analyzing and reassembling broken bones. And these are the sites that they're particularly interested in are very ancient human sites. So in Africa, around 2 million years ago, and then particularly one in the Republic of Georgia at Dominici, which is about 1.8 million years ago. Most people call it the oldest non-African site. There are some Chinese sites that are controversial whether they're older or not, or whether they're even human sites. But anyway, so what they're very interested in is, of course, analyzing what humans were like there. This is another article that came out a couple of years ago in 2017. You may have noticed where they excavated some mastodon bones in Los Angeles, and based on the pattern of breakage, concluded that humans were in the Americas 100,000 years earlier than previously expected. But then I just saw, just as I was preparing these talks, April 10th, 2019, that those breakages may have been caused by construction machinery running over the site before it got excavated. So the controversy is very there. Anyway, so what we're interested in is understanding whether the bones were broken by animals or humans or maybe natural forces. And so what we've been doing, and then there are all sorts of implications about brain development. When did humans become meat eaters? Were we scavengers versus hunters with social implications and so on? And the hypothesis is the geometry, the breakage will tell us who the actor, who broke it. And so we're taking bones. Right now we haven't analyzed the bones in the sites, but we're assembling a large data set of broken bones, some of which have been broken by students over in anthropology using Stone Age tools. So every so often they'll have a bone breaking party where they're whack bones and so on. And others are being fed to Scruffy the hyena who lives in the Milwaukee Zoo. Does a very good job of breaking the bones. And we're getting quite good results. So I don't have time to go through this. I just want to show this. This is a goniometer. So this is the state of the art up until recently in the subject. So goniometer is a means of measuring angles. And this picture I took in the museum in France, the Gem Museum, and it was used in the beginning of crystallography. And so the hypothesis is the fracture angles based on goniometer measurements do tell people something about the agent of breakage. Now we found that so there's a bunch of things there. There's problems with it. We have a virtual goniometer we've developed now, but what we've actually found is the thing that does the best job so far, and there's some sort of basic machine learning algorithms underlying this, are methods based on analyzing principal curvatures and spherical volume invariance. So that's where we are right now. We're still quite a ways away from reassembling the bones, but that's part of the project. It's ongoing. So I think I should end there.
So going back to the first half of the talk when you were talking about curvature, so you mentioned that it's very complicated when you have a projective transformation of a curve to compute the curvature, or there's some complicated relationship. But there's a theorem that's very important in human perception about that the sign of the Gauss curvature, the Gaussian curvature, which you mentioned in 3D, is the same as the sign of the projection of the surface, the outline of the surface in 2D. So the curvature.
There's some wonderful theorem through the Kundering about the connection between the principal curvatures of the 3D object and the curvature of its projection.
Right, that's what I was referring to.
Yeah. So I've been looking at that from this moving frame point of view, and I have some preliminary stuff, but nothing I've written down yet. That's a very interesting direction of research of the relationship between differential invariance in 3D and their 2D projections.
Right, because the perceptual system has the curvature in the plane, but of course is more interested in the 3D curvature.
What's your opinion about multi-scale curvature? This is a method that I once looked at. It monitors inflection points along a curve at different smoothing conditions. So in the original curve, there is inflection. It's very jagged, inflections are everywhere. And then you put the scale on y-axis and the inflection points on the x-axis. And And so the inflection points kind of do this. As you smooth the curve, the inflection points move closer and then they disappear. And then, so one characterizes the curve as the position of these extreme points. At what smoothing the inflection point disappears.
Yeah, I actually have a wonderful movie, but it would take me too long to find it. So we like to look at that in terms of the signature. So the inflection points are where the signature crosses the kappa axis. And so what we find is if you take a very rough curve, initially the signature is just a giant mess of string or whatever. But it very quick, so we do it under the curve shortening flow, where you move in proportion to curvature. So that's a very classical flow going back to Gage and Hamilton. And so it's used in many places. So you at each point in the curve you move, you smooth by going in the direction of the normal in proportion to the curvature. So if it's less curved, you move less. If it's more curved, you move more. And there's a lot of interesting math theorems of that. And what we find for that particular smoothing is after this initial mess sorts itself out very quickly, the structure of that signature is remarkably stable. Even when the curve is shrunk down to almost circular, you still see remnants of these, the inflection points, the zeros of kappa S, persisting, and the number of times it wraps around. So I'll dig up the movie and I can show it.
Yeah, I think that, yeah, that's very interesting. Yeah, I think it matches some of our neural representations here, the curvature and how much you integrate that.
So you see the sort of after all the high frequency noises basically gotten rid of, the main features of the curve are remarkably robust. Smoothing, even to the point where it looks circular to your eye, and the signature is very tiny, but it still wraps around and still captures what it had seen much earlier.
As you said, is that because you've now removed the high spatial frequency components and you're only looking at now the low frequency components, which are a lot more robust?
Partly, but the fact that it persists after the high frequency disappears is a bit surprising. We have some theoretical explanation, but it doesn't completely explain what's going on.
We're going to have to actually go on to the next talk, but you guys will have a chance to ask Peter more questions in the break. Thank you very much.